Okay, so first we'll consider the vibrational contribution, okay, mm, to the thermodynamic properties for a diatomic molecular system. Okay, so for that, eventually we will find that most of the molecules remain in their ground state at room temperature, and how their properties, at least the specific heat contribution, how it looks like, we'll see. So for that, let us first come to the energy level values. So we know that vibrational, so we are looking for Q vibrational equals to what? That is the question. So for that, we know the vibrational energy levels, okay, vibrational energy levels that you already know, because according to harmonic oscillator model, it depends on one quantum number, and that is the vibrational quantum number, and that is V plus half h nu, okay, where this vibrational quantum number can be 0, 1, 2, etc. And the frequency, fundamental frequency nu, that is 1 by 2 pi root over k by mu, right? So k is the force constant, mu reduced mass, you know all this. So we are using this expression to find out Q vibrational. So Q vibrational can be expressed in terms of e to the power minus epsilon v by kt for all v, right? V equals to 0 to infinity in principle. So given this, if we substitute this expression and then take away the e to the power minus h nu by 2 kt term, okay, you substitute this and then take away e to the power minus h nu by 2 kt, and then it becomes v equals to 0 to infinity e to the power minus h nu v by kt, right? Now given this, we can say, suppose here if you consider e to the power minus h nu by kt as your x, then this summation essentially is x to the power v equals to 0 to infinity, and that is equals to 1 plus x square and so on, and that can be written as 1 by 1 minus x. So this expression eventually comes as e to the power minus h nu by 2 kt divided by 1 minus e to the power minus h nu by kt, and that can be written in terms of another parameter, and that is e to the power minus theta vibrational by t, 2t, sorry, this is 2t divided by 1 minus e to the power minus theta vibrational by t, where theta vibrational is now what? Theta vibrational is equals to h nu by k, and it has the dimension of temperature, so this is the vibrational temperature of the diatomic molecule of consideration. So given this, Q vibrational has got a nice closed form structure. Once we have got that, we can then, let me write it again, that Q vibrational is equals to e to the power minus theta vibrational by 2t divided by 1 minus e to the power minus theta vibrational by t. Now given this, we know that q is say q will have q to the power n by n factorial, and out of which if we eventually go to the vibrational contribution part, that will be just ultimately, if you just substitute it, you will find that vibrational contribution to energy, that ultimately will come out to be nkt square del ln q vibrational by del t with nv constant. How do you get that? Just try to get that from using the whole thing here. It is just very straightforward. Okay, so once we have got this, you take ln of this quantity, log of this quantity, and then take the differentiation with respect to temperature, and then multiply with nkt square, and you can find out that ln of this will have, so essentially it is nkt square del t of minus theta vibrational by 2t, and then ln of that is this, and then minus ln of 1 minus e to the power minus theta vibrational by t, right? Something like this, right? So it turns out to be this. Now if you do the differentiation with respect to temperature and ultimately multiply with nkt square, we will get nkt, sorry, t square will go cancel with this t square that eventually come, so it becomes nk into, from here it remains as theta vibrational by 2 plus, because it becomes 1 by minus 1 by t square, and that t square gets cancelled, so minus also goes, and then eventually plus, then this one will give you theta vibrational by e to the power minus theta vibrational by t minus 1. So you can work it out. That turns out to be this. So this becomes the vibrational contribution to internal energy for a system of diatomic molecules, n number of diatomic molecules, and then the internal energy has a vibrational contribution because coming as this. Given this, naturally you can find out what is the vibrational contribution to Cv for such a molecule. Okay, so for that, if you consider molar quantity, that means n becomes n0 by Avogadro number, then this you will find is nothing but dE vibrational by dt, and that turns out to be, this part is, see, you are differentiating this with respect to temperature and you are putting n equals to n0. That's all. That means n equals to n0 means this becomes r, n0 into k, that becomes the universal gas constant. So this part does not contribute in the differentiation, so ultimately this is the part that remains, and then when you differentiate this, you ultimately get that this part gives you r, and then you have theta vibrational by t whole square. Okay, that is whole square, because from here also you will get theta vibrational by 1 from will come from there, and then 1 by t will differentiation will give 1 by t square, so it will be like this, and then e to the power minus theta vibrational by t divided by something like turns out to be